All right, so stats. That's what we're going to do today. It should be a pretty easy week because statistics, not too bad. Overall, nice job on the assessment. Nice job on the assessment last week overall. Make sure this week you at least try the problem a week if you're not doing that. Because again, it's preparation for you, right? For the HL or SL test. Other than that, let's see. What else do we have to talk about?
We won't be here tomorrow, juniors.
Oh yeah, what is it, ACT?
Yeah.
Oh, good luck. Good luck.
Seniors won't be here on Thursday.
Seniors won't be here on Thursday. Jeez, busy week.
Yeah.
Okay, well, is there anything you want to say before we start?
What do you mean?
I don't know, is there anything you want to say? Or?
Since so many of us are going to be gone tomorrow, are you going to put the notes on Schoology?
Yeah, so I've been making like videos and like, so right now I'm making a video and then I post that and then, yeah. All right. So we did some stats in Calculus 1, right?
Yeah.
And we did some stats in Algebra 2 and Pre-Calculus. Probably, right? So I'm not going to teach you how to do a histogram. You know how to make a histogram, right?
That's the thing.
Frequency, right?
We might need a refresher.
Yeah, I definitely.
Just quick drawing.
Okay. Histograms don't have any space,
Yeah.
right?
Oh.
Yeah.
There's a range of values here. All right, there's a range of values here. These are called your bins. And then you have frequencies, right? That's going to be some percentage. This one maybe takes up 40%. Maybe that one's 50, 30, blah, blah, blah. Frequency diagram, histogram. You know how to make those, right? I don't think I want to spend too much time teaching you how to do stuff you learned in Algebra 2. Let's see, what else? I'm not going to teach you how to calculate mean, right? You know how to do that. I'm not going to teach you how to do, let's see. Well, let's just see what we are going to teach you. All right.
I want to do.
Okay, so unfreeze this. Lila, sorry we missed our speech tournament on Saturday. That was annoying. Okay, so here is some information you have to get down. We're going to talk about discrete random variables, and when you see a random variable, it's always going to be capital. So for example, capital X, capital Z, capital whatever you want. It's just talking about the number, possible outcomes which could occur for some random experiment. So you're going to have a whole different bunch of X values that could be in this random variable. You flip a coin, maybe 0 represents head, and then 1 represents tails, right? So the random variable t would represent that coin toss, and there's only 2 outcomes, heads or tails, 0 or 1. Okay, so that's a random variable. Here's some important stuff for probability and statistics. All right, so just kind of put it into your own words, but these 2 things should be verbatim. These 2 characteristics should be verbatim. while you're writing, maybe somebody give me an example of another random variable. I gave you one of a towing cost. You give me another one.
Costs.
Coin toss.
Is that what I called it? A coin toss.
Pulling
Pulling
something out of a hat. Like something.
something in a hat. Yeah, like maybe there is, I don't know, 5 cards. 1, 2, 3, 4, 5. Right, or ace, 2, 3, 4, 5. Pulling something out of a hat would be a random variable. Your possible outcomes are whatever those cards are. Ace, 2, 3, 4, 5. That one would be a uniform distribution because each of those cards are equally likely. These are just 2 important characteristics of probability distributions, or statistical distributions. Well, probabilities have to be non-zero, and they also have to be less than or equal to 1. If something has a probability of 0, I don't care about it. Other axiom you would say is that if you sum all the probabilities in your random variable, so if you sum all the probabilities for the different outcomes for your random variable, well, if you sum all of them up, you should get 1, or 100%. Okay, so that should make sense. Any questions about this? We're good. No? Okay. Is everybody done writing, or do you need another second?
Another few minutes.
Oh. So we're only doing discrete today. So let's just think while let's just brainstorm. Give me some discrete versus continuous random variables. Give me an example of a non-discrete one, a continuous one. Okay, time, something involving time, or maybe height, yeah, weight, right? Age, right? All of those are continuous. Discrete, right? They have to be countably infinite.
Number of teeth.
Say it again.
Number of teeth.
Number of teeth. As you get older, the number of teeth you have decreases. Yeah, it kind of goes like that, right? You lose some, it goes up, you have the maximum, and then at some point it starts going down because you eat too much candy.
And you get fake teeth.
Then you get fake teeth. All right. Take another 20 seconds, scribble down some notes. If any of you ever want to take the Chapter P exam, like if you're thinking about actuarial science, right? Let me know, because that one I can tell you all about, and I can tell you some good resources to help prepare you, to make sure you get a passing score on your first attempt. And if you're interested in making a good, decent amount of money, right, actuarial science is a good way to do that. And there's lots of applications. You can do insurance, you can do health field, you can work for the government, lots of different options. Okay, so this example, x is a random variable representing the number of girls for a family of 3 children. Write down in table form the associated probabilities for each x value x may take. Before you attempt these type of problems, you should reread what x, the random variable, represents. What does it represent?
Number of girls.
Number of girls. So what are the possible outcomes it could have?
Where, girl?
0, 1, 2, 3. You find out the associated probabilities for each of those. Hey, Jay. A tree diagram might be good here. Tree diagram would be good. Combinatorics would be good. Table. You got 3 different options. problem with tables are is that they get really big really quick. But that's fine. And with any luck, when I count these, there should be 8 of them. 2, 4, 6, 8. There are, and now I have the probabilities. Probability of getting 0 girls in a family of 3 children is 1/8, 3/8, 3/8, 1/8. Okay, so there's our first discrete random variable. For having 3 children, assuming boy or girl is equally likely, which actually it's funny, it's not. Here's your distribution, right? All boys, 1 girl, 2 girls, all girls. Okay? So it's important to contextualize these so you make sense of them. Everybody good with that? Yeah. All right. Let's see. Here's another one. Random variable x has this distribution shown. Random variable y is the absolute difference between 2 events in x. Create a probability distribution for y. So sometimes you want to look at random variables which are combinations of other random variables. And this is an example. So random variable y is the absolute difference between 2 events in x. So let's calculate all the possible outcomes for y. Well, what's one possible outcome if you take the difference between 2 of these events? You could have 0, right? 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4. Another one would be, right? 2 minus 1 would give you that, 3 minus 2 would give you that, 4 minus 3 would give you that. 2, 3 minus 1, 4 minus 2. I bet 3 is 1 too, yeah? 4 minus 1 is 3. All right. And I think that's it. Can't have anything else. So, for these things to happen, let's see what would be the probability, for example, 0 coming up. 0 would come up if you had first chosen 1, and then you also chose 1. That would give you 0, right? 1 minus 1 would give you 0. Okay. Another one would be 2, 2, 3, 3, 4, 4. Those would all give you 0, right? Well, what's the probability of choosing 1 and then choosing 1? 0.1 times 0.1, right? So this would be, have an associated probability of 0.1 times 0.1. This one would have an associated probability of 0.2 times 0.2, 0.3 times 0.3, 0.4 times 0.4. Well, guess what? What is the associated probability for 0 then? What do I have to do with all these numbers? There you go. Find out what that number is. You tell me. I got somebody telling me 0.3. Let's get some other verifier. Yeah, 0.3. Correct. Okay. You got the wrong ones? I got 3 people telling me 0.3, so I
Yeah, that is actually like that.
Yes.
Yeah.
Next easiest one might be to find maybe having a difference of 3. Having a difference of 3, because there's only one option that would give me that, right? 4 minus 1 would give me 3, so it's 0.4 times 0.1. And that's equal to what? 0.04? You find the other two. You find 1 and 2. So work together so you can check each other's work. Find 1 and 2. What did that one add up to? Ooh, something's a little bit tricky about this one. I could either choose 2 first and then 1, or I could have chosen 1 first and then 2. Or I could have chosen, for example, here 3 first, then 2. Or I could choose 2 first, then 3. Same thing here. All right, so forwards, backwards. That should account for all the different options, right? Do you agree? Yep.
Would that mean then for the difference of 3, that would be 0.04 plus?
Yes. So that would be plus the other option, so that would have been plus another 0.04, so that would have been plus 0.08. Yep. So that's what's going to happen sometimes in probability. You're going to ignore something, and then you're going to have to come back and rework. So what did that add up to? You got 0.4? 0.4? We got 2 people telling me 0.4. Anybody else? You guys have to be calculating. I need multiple people telling me. 0.4? Well, let's see. If we did this correctly, but we're going to verify by doing it by hand, what should this one be then?
0.22.
You should get 0.22, right?
Yep.
So verify by hand that we get 0.22. Verify by hand that you get 0.22. Did anybody already verify by hand that we get 0.2? Yeah. Okay. Does it make sense why you would have to get 0.22?
Does it add up to
Let's hear it.
1?
There you go. All right. So we're good with that?
I thought it just had to be less than or equal to
Well, that's for each associated probability.
1. Oh, okay.
Each x value, or for this one y value, has to be less than or equal to 1. Good? 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 Good. All right, so let's move on to another example here. Got a bunch of fun ones today. Here's an easy one. What's the value of t? 1 minus the other stuff, right? 0.54
0.33.
plus 0.13
0.23.
is 6, 7. Oh yeah, 0.23. Oh, look at that. Mr. Anderson already had us covered. All right, 0.23. All right, that one should be pretty straightforward. Okay. How about this one? Are you going to find the value for each associated outcome? You need to use one of the axioms from probability, which is all the associated probabilities sum to 1. Sum of all my yi's is equal to 1. C plus 2c plus c plus 3c equals 1. I think that is 7. C equals 1/7. So our table then, 1/7, 2/7, 1/7, 3/7. Go with that? See, that's why stats is fun. It's so easy, right? Till it gets difficult. All right.
Next slide will be like,
Can I move on from this one?
how do you use with
Okay. There's two axioms that you have to use to be able to show that each of these are probability distribution functions. So verify that both of these will satisfy both of those. So verify that both of these are distribution functions. You have to verify that each probability is non-zero and that the sum of all of them is equal to
1?
There you go. That's how you prove it. You do the first one, and then we'll do the second one together. Or you can do both by yourself. Either way, I'll do both up here. Okay, so there's a table. Let's see, 27, 32, 34 to 34, sum to 1, check. Each probability is non-zero, check. It's a PDF, check. Probability distribution function, it's PDF. Good with that? Okay. How about that one? That looks confusing. Let's check. Okay, so notation here. This isn't too standard notation. Usually what you would see is, if you don't recall what that is, that's just 3 choose x times 0.6 to the power of x times 0.4 to the power of 3 minus x. And that's for x equal to 0, 1, 2, 3.
I'm sure we have those in our calculators somewhere. I just can't.
Yes, so let's double check.
Math
It's
and
easy to do by hand.
Binomial,
math.
NPR, NCR.
Math.
ERB.
Yep, so math PRB 3 if you're using the TI-84. Or just Pascal's triangle, right? Let's see, 3 choose 0 is going to be 1. Let's write down our table actually. Oof. What just happened? Oh. Well, find out those numbers and then we'll write them down. So it's 3 choose x, 0.6 to the power of x, 0.4 to the power of 3 minus x. Okay, so 3 choose 0. Well, that's just 1. 0.6 to the 0 is 1. 0.4 to the power of 3 minus 0 is 3. So what's 0.4 cubed? 0.064? 0.064. All right, thanks, Kip. 1. Let's see, 3 choose 1 is 3. 0.6 to the first, 0.4 squared. What's that number? I'm just evaluating p of x. Calculators?
36 over 125.
36 over 125? Sure, let's use that. Nice and exact. 36 over 125. All right. 2. Well, 3 choose 2 is the same thing as 3 choose 1. 3 times, well, let's see. That is 6 over 10 squared. 6 over 10 squared times 4 over 10 first. So that's what?
54 over 125.
54 over 125? 54 over 125. And then what was 3?
27 over 125.
27 over 125. With any luck, this should all add up to 1. Does it add to 1?
Yep.
There we go. Got my human calculators in here. This is good. All right. Sums to 1. Each probability is non-zero, so you're good. Easy peasy?
Lemon squeezy.
Lemon squeezy, right? All right. So we like that example. Those are the ones that are easy. Now we try some more. Let's see. Oh, here's a good one. Okay. Let's bring it back to Algebra 2. Let's get a reader. Lisa, let's get you to read.
Suppose the women's basketball team bus carries 5 starters and 7 reserves. A random group of 3 players gets off the bus. Let Y be the number of starters that get off the bus. Find the probability distribution for Y.
All right. So you guys work together. See if you can come up with the probability distribution for Y for this problem. See if you can do that together. I'll draw a picture up here and then I'll do it.
What is hypergeometric?
Hypergeometric is just a special type of probability distribution function, and that's what this one is. So you'll see the, we might talk about the form of what those look like, but that's what this one is, if you want to look it up.
So it could be 0, 1, 2, 5. There's only 5 stars. To start off. There's a 41% chance that it started. There's a interesting looking school bus. Basketball. 5 starters.
Well, let's see. There's a little bit of a problem. You have to account for people getting off. So there's 2 things. You have to account for people getting off, and then what that does to associated probabilities. So, how many people got off the bus? 3. So what are my associated values for this probability distribution function?
0, 1, 2, 3.
0, 1, 2, 3. So you have to calculate each of these. So what's the probability that 0 girls get off the bus? Well, oh, sorry, 0 starters. Okay, they're all women. So probability, non-starters. Let's see, non-starters. Non-starters, how many do we have?
7.
Yeah, 7, and there are 12 total, right? Starters, looks like you have 5. So, probability that 0 get off the bus, well that's 5, let's see, we have 7 12s, that's a non-starter, times, or sorry, plus, no, not plus, this is a good thing to think about, is it adding or subtracting, or sorry, adding or multiplying, 7 12ths times 6 11ths, times 5 10ths, right? Non-starter, 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 right? Okay, well for the other one, now 1 starter gets off the bus. How many different ways can that happen? 3, right? 3, choose 1 times. Well, let's say the first person was a starter. The first person was a starter. What's the probability that happens? 5 12ths. Well, the next person who gets off the bus needs to be a non-starter. How many of those are there? I'll tell you in a second.
7 1.
7 out of 11. The next person also needs to be a
Starter.
non-starter.
Non-starter.
6 out of 10. So, number of people on the bus, 12, then 11, then 10, right? One person gets off, then another, then another. Well, let's say the first person was a starter. Probability that happened is 5 12ths. Next person gets off needs to be non-starter, 7 11ths. Next person who gets off, 6 10ths. Well, how many different ways can this happen? 3, right? Could have been this person, and this person. So that's my thinking here. Does that make sense? Yep.
So all the numbers, the denominator, it all comes out the same because
Well, let's double check. This is just my first initial thought. I didn't work through this problem yet. This is my first initial thought. It could very well be that maybe we might get a different number if we do 5 12, 7 11, 6 10s, plus another option would have been 7 12s plus 6 11s, times 6 11s times 5 10s, plus the other option of 7 12s, what would the other option be? 5 11s times 6 10s. Does that make sense?
but what if because the denominators are going to be the same because you're just losing 3 people overall,
Yeah.
shouldn't and like multiplication is negative, so how should that affect that?
We should get the same number.
Yeah. So
Is
do
what
we
I'm-
need the 3 1? The 3 choose 1?
Oh, well, yes, because there are 3 different cases.
Okay, cool.
Yes. Let's check for this one. 3 choose 2 times associated probability. Well, let's see. Let's make sure we keep it in order here, just to make sure if we can see if any errors happen. First person gets off as a starter. Next person who gets off as a starter. Next person who gets off is a non-starter, and that is, how many do we have left? That would be 7 out of 10. If we did this correctly, there's only one way for all 3 of them to get off the bus. Well, let's see. Associated probabilities would be 5 12ths times 4 11ths times 3 10ths. Now, with any luck, these should all sum to 1. So let's check. Should be calculating. It worked? There we go. Spoiler. All right, nice job. Plus 3 times 5 divided by 12. All right, I agree. Anybody else verify it? All right. So you can see sometimes calculating these probabilities can be a little tricky, right? So that's the sticky thing about probability, is counting is the most difficult thing in math. Counting the possible things that can happen. That's no joke. All right. So, ready to go on? Okay. So this one, again, if you're interested in looking up, we might have a little bit of time to talk about the different distribution functions that are interesting. Talk about them in here. But if not, look them up as we go through. That one's called hypergeometric. How many of you remember doing expected value? Some? Okay. Well, good. We get a review again. Expected value, same thing. Not really the same, but calculations are pretty close. Same thing as when they say expected value, you should think mean, right? Okay. Expected value. Values of a random variable multiplied by each associated probability, then added together. Expected value is just the sum of all the probabilities times by their respective outcome in that probability distribution. Oops. Cheating. So when you get that written down, find the expected value for this probability distribution. The notation is kind of weird in your book. Most texts would write it like that because it's a little more clear. Anybody calculate it yet? Oh, okay. Sure. Let's list off all of our xi's. x1, x2, x3, x4, x5, right? So this is 1, this is 2, this is 3, this is 4, this is 5. So those are each of my xi's. What are their associated probabilities? P of xi's. Well, P of xi for 1 is 0.09. So the first term in this sum should be 1 times 0.09. Second term in the sum should be 2 times 0.21. Second term in the sum should be 3 times 0.47. 4 times 0.22. 5 times 0.01. Good? Anybody calculate it yet? You got 2.85. Okay, and look at this. If you look at the distribution, I believe you because in between 2 and 3 is the majority of your data, right? 21%, 47%. So that means, and this one's 22, so it should be going this way. The mean should be going this way. So yeah, 2.85, I believe that. Let's just double check. 2.85, anybody else? Yeah. And here were the calculations. 1 times 0.09, 2 times 0.21, 3 times 0.47, blah, 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 2.85.
So that's E of X.
Say it again.
So that's the E of X.
Yeah, expected value. This is the mean. Is mean always going to be a good measure of central tendency? No. Why? Right. It's susceptible to outliers, right? So it can be skewed because of those outliers. So you want to always look back at your distributions and say, should I use the mean? Should I use median? Right? What measure of central tendency should I use? So that's what you have to think about when you're doing statistics. Ready to go on? Okay. Okay. Oh, Mr. Anderson's cheating us. Let's see here. Let's see. Do these have? I added some slides in here. Let's see if they're still in here. Okay, well, while I'm looking to see, because I had some extra examples I want to go through, find these out. Find out what A and B are. Okay? Say it again. Oh yeah. See, that's why I knew something was wrong because I had switched these up. Shoot. Well, you find out how to find them. All right. Talk about it with your partners. Find A and B without cheating.
Set up two equations. Oh, I know what to do.
There we go.
What do we? I have an idea.
There it is. Okay, good. So last two examples. Let's see. That's 0.9, that's 0.1, so that's 1. 3 minus 1 is 2. So you should have had two equations here. A plus 2b equals 1, and a plus b equals 0.6. Yeah? And then when you solved it, what did you get for a and b?
Oh, B is 0.4, A is 0.2.
0.4, a is 0.2. And let's check. 0.4 and 0.2 is 0.6, 0.7, 1.0. Still have a probability distribution function. Oliver?
I got
Opposite?
I agree with
Yeah, if you keep everything in line, this should work out. I didn't do it though, so I'm just trusting you. But did anybody else find this?
I got the B equals 0.4.
You got that.
B equals 0.4 and A equals 0.2.
So I'm guessing there was something about how some of us are typing it in that might be affecting it. That'd be my first guess. Hey, John. Thank you. Okay, so before you leave, I had one last problem I want to do together. One last problem I wanted to do together. Okay. So, yeah. So some more problems with, but no differential equations this time. Okay, some of you might have remembered this from Calculus 1. Electrical components are produced and packed into boxes of 10. It's known that 4% of the components may be faulty. Random variable x denotes number of faulty items in the box and has this probability distribution function. Find the probability that a random selected box will contain no faulty components. So since we won't have enough time to finish this, what is that asking you to find? Find the probability that x takes on what value?
0.
There you go. So you're going to find out what is the probability that x is equal to 0 for this one. What about for this one? Find the probability that a randomly selected box will contain at least one faulty component. Probability that x takes on values greater than or equal to 1. Here's where you have to use a little. So this is equal to, let's see, 1 minus probability that x takes on values less than 1. Well, the only value that's less than 1 is 0. So this is equal to 1 minus probability x takes on 0. Sometimes something is very difficult to calculate in probability. This happens a lot, but other equivalent ways of writing it are much easier. Right? This is using the fact of complements. Right? This plus this equals 1. So 1 minus this should be equal to that. Right? This is complements. Can you do this on your own? Yeah? I think so, right? Evaluated at 0, 10 choose 0 is 1, 0.04 to the 0 is 1, 0.96 to the power of 10, that would be your probability, x equals 0. What was it? Why don't you calculate it? Your homework this week. Well, for due Wednesday, Schoology, right? Since it's statistics, I like it a lot because I have all the questions listed in Schoology, selected ones that I chose. You're going to enter your answers on there, and then you get instantaneous feedback if you're doing it right or wrong. Right? So that one's due Wednesday, and it's just what we just covered today. That sound doable? Yep. It's about, I think I selected like 8 problems to do in Schoology. Say it again. I think I might have put 2 attempts in there. So yeah, if you type something in incorrectly, then you would have a second time. Go back.
You can only do it once.
So I think you're going to attempt it twice.
Like, you do it all in one batch.
Yeah.
Oh.
Yeah. I think I have them. They might either be individual questions or they might all be in one. Yeah. Just double check. Should be pretty quick.